Welcome to the online MOOC course in software engineering. In this lecture, we will be looking into software reverse engineering. This is the contents. So, we will learn what software reverse engineering, what is the need for this reverse engineering, the core activities that will be performed, followed by the rules, tools and usage, and the risk and ethics dealt with this. So, before we go into reverse engineering, we have to recall what we have done in forward engineering. So, in forward engineering, we had main 5 steps. So, first one is requirement analysis, second is design, third is implementation, fourth is testing, and fifth is maintenance. Okay. So, in the requirement analysis phase, we will try to understand what is the requirement from the customer or any other stakeholder, and we will try to make a contract, and that will be saved under SRS, software requirement specification. So, once the requirement is done, we will go for the design phase, where we will try to identify the ways in which you can implement. So, here most of the time we will be using some diagrams to identify the methodology. We will understand the requirements and try to propose a solution to implement. So, we have learnt many techniques like drawing a DFD and use case diagrams, many other things we have learnt in your design phase. And the third one is the implementation. So, once the design has been completed, we will be trying to go for the implementation. So, based on the project, based on the software that you are going to develop, you will select a programming language and try to implement that corresponding software. Okay. So, once it is implemented, you will go for testing. So, testing is a phase where we will try to check whether the implemented software is valid with respect to the requirements or not. Okay, and also we will try to verify the correctness of the code without any logic errors or any other problems. So, this is the idea of testing. So, once all the things with respect to the software development life cycle is done, you will deliver that corresponding product to the customer, and after providing that to the customer after production, if there is any problem, or you will be trying to provide some maintenance in their premises, which is called as software maintenance. So, this is going to be the cycle that was followed in SDLC, and there was many process models we have learned. So, which starts with waterfall model, prototyping model, incremental model, spiral model, agile model. So, I will take 5 models for simplicity. There are several other models, and these are the major important models. So, what we have learnt in waterfall model, so you have to move from one stage to another, and once you have completed one stage only, you will go to the next stage. So, there is no way to go back to the previous stage. So, that is what is waterfall model. In prototype model, since we have the drawback in waterfall model, like you cannot go back if there is any change, there will be a prototype that will be developed. So, that is not the actual code or actual product, but you will try to build a blueprint. So, that blueprint, if it is satisfying the customer, you will start building the regular product. Okay. So, that is what is called as your prototyping module, process model. And in incremental model, you will not develop the entire project as one single stretch. You will divide that into modules, and at each iteration you will try to develop one working functionality. So you will add on the module such that the functionality gets increased day by day. So maybe at the last increment you will deliver the entire product. So that is what with respect to your incremental process model. So in all these models the introduction of risk is not being dealt, but in spiral model it is trying to add the risk assessment at each and every phase, so that if some risk are been identified, they will provide solution for that risk and go back in the spiral fashion. And all these are conventional waterfall models, where conventional process models where it will not have much importance with respect to day-to-day programming or day-to-day requirement change. So that is given in agile methodologies, which is now widely used. So in whatever models that we have learned, you will move from requirements till your testing, or requirements, then your design, implementation and testing. We will forward in this direction. So those kind of engineering is forward engineering, but now we are going to learn something called as reverse engineering. So which means that you are going to travel backwards. Okay, so from the executable source code, the implementation, you are trying to find the design. From the design we are trying to find the specification. From the specification we are trying to find the high level requirements. Okay, so this is what we call it as reverse engineering. You are trying to go backwards the phase and try to identify for what we have actually done this. Okay, so you might have a code in hand, but what was the design document to which I have this piece of code in my hand? What was the specification to which I have this design document or the design in my hand? So that is what is the idea. So this is what is reverse engineering. The main problem comes to why actually we need this reverse engineering. The simple solution is that you might have a very old software that was working many decades back. Okay, in such scenarios the documentations will not be available. So when you have an executable code in hand, we are trying to backtrack and find what was the design and go back further and find what was the requirements. So when you have something in your hand and if it is not working properly, or you want to upgrade to a newer environment, or if there is a threat in that corresponding software and you don't have the prior phases, this reverse engineering is trying to provide you that insight. That is all about your reverse engineering. So this is a disciplined process of analyzing an existing executable. In case if you have a code, to reconstruct. So from the executable code we are going to design architecture and the components, requirements, all these are going to be identified just because they are absent or obsolete. Okay, so it proceeds backwards. So as I said, you have the code in hand and you are going backward and identifying the need why you have actually developed this corresponding code. Okay, so it proceeds backwards from the implementation artifacts to higher level abstractions. So this enables the engineers to regain the lost knowledge and support the downstream activities like maintenance, migration and security assessments. So this is what I was trying to say. Assume that you have a very old software that is working fine, but you are in a maintenance phase. So you have been given that software to maintain. So to maintain a particular software, you have to understand why actually it was built and for what reasons they have built this corresponding software. So you need to go back, reverse engineer and find the requirements. Again, migration. So sometimes your software might work in a specific environment and you want to migrate that to a newer environment. Okay, so in that case also you have to reverse engineer and find where all you have to modify in the existing code. So by doing that also it will be easy for migrating the code. Third one is security assessment. So sometimes in the today's world you get some viruses or the data may be hacked. Cyber threats it is common nowadays. So in that case, if the software has been bugged by some other people, a competitor or anybody, so you have to make sure that from where this has to be cleared on. So if there is a bug, there is a loophole in your code. So to find that loophole, you have to go back and check where exactly the problem is and then refactor from that point. So this is what is reverse engineering. So you can either have a source code and go to design. So that is also reverse engineering. Second is from design to specification. Third is from specification to the high level requirements. So these are the necessities. So why you are trying to do the reverse engineering. So first and foremost, as I said, to understand the legacy system. So you have a very old system which is still working, but you don't have any documentation in hand. So you can do the reverse engineering. Thereby from the code you are going to find the design, and then from the design you will try to find the specification, and then you will find the requirement. So basically that is what is understanding the legacy system. So why we are going to do that? We are trying to maintain whatever that is available. Second one is specification recovery. So sometimes the specification documents, some documentation might get missed. It could be like missed in some catastrophic efforts, or by nature you can also delete some of the files. Okay, so in that case you can do this specification recovery. So specification recovery is something like from the design document we are trying to do a reverse engineering and find the requirements. The third one is security analysis. So as I said in the previous slide, you have a software in hand and there is some bugs, some vulnerability is there. So what we mean by a vulnerability? That is a place where any other external force can enter the system and do some modifications or just take some data from that corresponding port. Okay, so to identify if there is any vulnerability or to inspect any malware. So if any other software which is external, which does not belong to your organization, they also might get installed within the software. Okay, so that and all could be identified only when you debug the code in your reverse engineering process. The next one is interoperability. So as I said, migration. So here the new systems has to interact with the old ones. Okay, so you have the old system, but you have built a new system and you want to communicate between these two systems. In that case also, only if you know how it is going to interface with the other set of systems, you can go forward. So interoperability across systems, one being new and one being old. So new systems we will be having everything in hand. For the old system alone, you can do this reverse engineering and find the interface mechanisms. The fifth one is platform migration. So this was discussed already. So outdated platforms could be changed to the modern platforms through this reverse engineering. And software maintenance, so any corrective or adaptive changes could be done for the existing software which does not have any prior stages of documentation. So these acts as a drivers that transform opaque binaries into manageable intellectual assets that reduce risk and extends the system life. So we call this as binaries. Why? Because we only have the executable file in hand. So sometimes from the executable file you have to extract the code and then move forward. Okay, so just a binary file will not have any meaning in the human eye. So from that we are trying to build an intellectual asset. So how we can do this reverse engineering? So first and foremost, assume that you have the code in hand. Okay, so not the binary, we have the source code in our hand. So from the source code, what we can do is we can identify and understand the low level details. Okay, so say for example, there can be many control flows. So you will be having while loops, for loops, many other loops, right? So these are trying to find the sequence of operations. Then we will try to find the data structure. So any program that is taken into consideration, we will have this CRUD. We have learned this already. So it will create something, read, update and delete. Okay, so this is normal for any database oriented application. So in that case, when you have a data in your project, how we are going to store it? What is the structure in which you are going to store the data, which is what we call it as data structure. So how it is being organized and how it is being stored. Okay, so that could be analyzed from your source code and what algorithms are being used. Okay, so in case if you are using a say stack or queue or tree or a graphical database, so what kind of algorithms will be used inside your programming. So we can understand that the same program could be solved in several algorithms, but which algorithm you are going to use is trying to solve the time or the speed in which you want to complete that corresponding software. Okay, so the algorithms is trying to discover the core computational procedures. And the fourth one is that, is there any dependencies with respect to another component? This component could be commercial component or another component that is built within the program itself. So when you have a program, a source code in hand, so assume that for a software, a legacy software, the source code will normally, it will be very big. Why I am trying to say it as very big is that nowadays we are using say Python and any other high level language. So it will be having many libraries and already available codes, right? So you can just include those libraries and you can perform a function in very limited number of codes. But earlier in legacy softwares and all, those options may not be available. So in that case they might have coded each and every part of the code so that the length of the code will be high when compared to the high level languages that we work as of now. Okay, so from that piece of code we are trying to find what is the control flow. So from the start of the code till the end of the code, you are trying to find the control flow graph. So we will say that as control flow graph or CFG for short. So it will be having graph kind of an activity, say for example like this. So if this is start and stop, these are some process, say P1, P2, P3, and you can have a control flow, say like this. I am just trying to draw it randomly. Okay, I have just drawn this. So from start to stop there will be many paths. Say for example from start it may go to either P1 or P2. So from P2 it can go to P3 and stop. Correct? Or from start it will move to P1, P2, P3 and then stop. Next is from start it can go to P2, P3 and then stop. So likewise there could be several controls. Okay, so the control will start from here to P1 and then P3 and stop. So likewise from the program you will draw a control flow graph and check what all the different path in which you are going to move. So this path may be based on the control. Say for example here you might have a if loop or a for loop, whatever it may be. So that when it going to true, maybe it will go to P3, if it is false it may go to P4. Just an example. Okay, so you are trying to identify the control flow. Second is the data structure, how you are going to save the data within each and every module. And next is the algorithms that have been used inside each and every functionality and the dependencies. So everything has been identified from the code. So from this you can actually draw a diagram. So now I have drawn a diagram, right, CFG. So this can be used for identifying what design it is. So if you remember in design we might have drawn a data flow diagram or a use case diagram. So you can convert this to a DFD. Okay, so from a code in hand we have moved in reverse and we have gone to a design phase. Okay, by identifying all these four things. Now from the design we have to go for the specification. Okay, so this is that process. So the design recovery technique. So here we are trying to reconstruct the architectural views by surfacing abstractions from code. Okay, so you will be having the modules. From the modules you are trying to find the data flows. This is what I was trying to say as data flow diagram. So data flow in the sense you are trying to check you have all the modules. So from which modules another module is going to be triggered. What is the information that is moving from one module to other. So that is what is being analyzed. And next is the interactions. So within the module we will be trying to identify the cohesive units of functionality. So we have already understood in the prior classes that in a software design a module should be highly cohesive, meaning it should be very much related to one single module. Okay, so when you have the modules you are trying to find the data flow, which is nothing but the mapping of the transformation and moving of data from a module A to B. Some data might need to be moved. So what are they? And a module may also trigger. Okay, I can tell you an example if you want. Say for example a library management system, you would need to borrow book. There is another module called as book availability. So when a user wants to borrow a book, this borrow a book may trigger book availability to check whether this book ID, say for example I am asking a book ID. Okay, so it will check whether this book ID is available or not. Only if the book is available, this person will be allowed to borrow a book. Right. So here there are two things that we are doing. One is passing the information BID, which is nothing but movement of data. Second one is this book, the borrow book process is triggering book availability to check whether the book is available or not, which is nothing but the transformation. So this is triggering another module. So the last one is interaction. It is trying to check where all the interaction is happening across the modules. Okay. So, it is trying to surface the object and the subsystem collaboration. So, where all it is been linked, that is what. So, by these scenarios, by these work, you can recover the design. Okay. And this is going to be done iteratively so that you can get better decisions. So, again you can also verify the design that you have generated after the reverse engineering with the code, so that it is matching perfectly or not, so that you can produce coherent models, so that further evaluation that can be used without any hindrance. So, now we have two types of analysis. One is static analysis and dynamic analysis. So, we are trying to again take the code in hand and we are going to identify whether we are trying to check for the design. So, now what we mean by static and what we mean by dynamic. So, static is without runtime. So, without executing, we will be checking the code for any problem. Okay. So, we will be trying to find the structure is correct or not, the code structure is correct or not, signatures and the potential flaws. So, what is actually signature? We normally call that as method signature. So, you will be having a return type, the function name, function or method whatever, followed by arguments. Okay. So, when you have a function should be having a name and the set of arguments that are necessary to work on this function, and after completing the execution of this function, it will return something. So, if it is going to return a number, this return type could be an int. Okay. If it is going to return a character, the return type should be character. Okay. So, as an example, I will say int check age Okay. So, assume that there is a logic return in between. It is going to check whether the age is greater than 18 or not, and if it is greater than 18, it is going to return 1. So, the return type is integer and the function name is check age and the argument is age. So, you can actually say int age, specifying that age is going to be an integer and your return type is also an integer. So, the signature is checking something like that. So, say for example, if you have returned a statement like int check age without any parameter, you are trying to make sure that there will be an error if you execute. So, the signatures will be checked and we will make sure that there should be some arguments and that will be noted and said at this static analysis phase. Okay. The examines the code structure and logic and it identify the coding patterns and signatures. So, this is what the signature is, and it also finds the potential vulnerabilities. Okay. So, vulnerabilities I have already said, it is the places in which the external entities could interfere into your program and do some unwanted things, say taking a data breach and all, or it may update some values within our program also. So, we are trying to check the vulnerabilities. On the other side, in dynamic analysis, it is done at runtime. So, this is at before runtime, here it is done at runtime. So, we will be having debuggers and profilers. So, they are another set of tools that are available. You can set debugging points in the IDEs and check whether you are retrieving the same value or not. So, it will give you the information if there is any abnormality. Okay. So it observes the actual program execution and it validates all the assumptions, everything is covered or not, and it also uncovers runtime specific behaviors which is not available in your static. So sometimes the code will be behaving and it will be like a working software, but at runtime there could be like many other issues that comes up. So you might have also experienced that. So you will not have any compilation errors, but you might have runtime errors. So that could be handled only through your dynamic analysis. So there is a hybrid approach also where this static and dynamic analysis is carried out in Fusion. Okay, so that is going to give you a comprehensive insight. So now the third is from the requirement, from the design we are trying to generate the requirements. So here the reverse engineering, now we will be having the design documents. So what are the design documents that we have learned? ER diagrams, class diagrams, if you are following the object oriented approach, or the structural approach will have your data flow diagrams. Sequence diagrams is your UML diagrams, and the architectural views. So now when you have ER diagrams, we will be having the entities, relationships. So from the entities and relationships we can very well understand who are all going to be the actors, what are all the process, how they are going to interact, what are the specialization, generalization, everything can be done. And if you have the class diagram in hand, you can know what are the attributes, what are the methods, and again there are some object oriented concepts inside. So from that we can very well understand what exactly you are trying to do. Okay, for what requirement they have drawn the diagram. Similarly, from the data flow diagrams you can identify the transformations and the process at various levels. So the data will be flown from the initial stage to the end. So that could be identified or that could be analyzed and understood from the data flow diagrams. Sequence diagram is with respect to time. Okay, so which user interacts to what process and the sequence in which you are going to interact. Okay, the flow of interactions over time. And the architectural view is trying to provide you a high level system structure overview. So now this set of diagrams you have in hand. So from that we are trying to reverse engineer and identify the requirements. So we can find the missing artifacts and close the knowledge gap and facilitate the stakeholder communication. So these documentation is going to serve as a reference. Okay, so basically from these set of diagrams we are trying to do a reverse engineering and find for what requirements they have drawn this diagram. So next is the tools that are used for reverse engineering. So there are some set of tools listed here. So the first tool, Ghidra, this is an open source, this is given by the government. This is mainly used to check if there is any cyber security related issues. So you can give the executable and get the source code out of it. Okay, and the second tool is very prominently used, which is IDA Pro. This is an industry standard, but this is a commercial software. You have to buy it and use that corresponding software. And R2 is also an open source platform. This is a little difficult when compared to the Ghidra tool, but it also comes with a UI which is Kata, with which you can try to reverse engineer a code for the scriptable inspection. And Binary Ninja is another tool where you can go for modern RE framework. This is a modern framework with powerful automation. And Wireshark is normally used in networks. So it is a network level protocol wherein you can discover and analyze the flow of packets from one node to another, with which we can understand the flow in which you are moving. So if your project is basically in a network perspective, not a desktop oriented, you can go for this Wireshark and identify the packets. So if somebody is eavesdropping or anything else, that could be identified here. So the basic idea of these tools is that when you select the best tool for the application, so any tool is not, there is no better and worse tool here. Selecting the best tool for the application will actually make your system very great, and it is going to be accelerating the comprehension. So where all it could be applied? Again, some application scenarios are being listed. So assume that there is a software, a legacy software, and there is a malware triage. Okay, so it is a we have to understand the threat and do the cyber security defense. Okay, and this is mainly used in forensic investigation, wherein there is a necessity for digital forensics in today's world. Okay, so without the knowledge or with the knowledge, you can introduce a malware in another person's environment. Okay, so you have to extract the evidence from that using these reverse engineering process. And the performance optimization, if you have any bottlenecks, like you are not getting better performance, you can also do this reverse engineering, find the fault and then rebuild from there. And the competitive benchmarking, so when the software has several other good competitors, again we can reverse engineer, refactor and then provide. So the main important application stands with malware triage and forensic investigation. Okay, there is a very important, urgent, necessity to address the malware. So in that case, this reverse engineering is going to give you much impact. So even we have this option of reverse engineering, where you are going to move backwards from the code to your requirements. There is some ethical and legal boundaries associated with it. So you cannot just refactor a commercial software that is available. So it is, we have to respect the copyright and licensing and make sure you don't do any reverse engineering for the commercial project. And you have to secure explicit authorization. A clear permission has to be obtained before doing this reverse engineering. So if it is within the organization, it is not going to be a problem at all. But if you are trying to do it for an software from a different organization or from a different people, you have to do explicit authorization and document the legitimate intent. So you have to maintain the clear records. So why we are going to do that, and everything has to be done, and it is we have to also limit the sharing to authorized stakeholders only. Okay, so many softwares nowadays we are trying to get the cracked version, so that and all is not legal and that has to be avoided. So as a summary, we have understood what we mean by reverse engineering. It is a sequential process, and what are all the tools that are available, and we have to make sure that these are ethically correct and only if it is within the organization. Okay, and once you have already gone through a signed contract. So in this lecture, we have learned what we mean by reverse engineering, why we need that, and the core activities in performing the reverse engineering, several tools that are available, and the associated risks and ethics in reverse engineering. Thank you.